Hey, welcome back to part 3 of your big kinematics equations. In this part 3 video, we are going to look at problem-solving skills using the kinematics equations. So, what I'm going to be doing, I'm going to go through a problem. I'm going to use these steps that are useful, good for your problem-solving skills. And after solving this problem, I will give you a chance to try yourself while afterwards putting myself on fast play to quickly go over the solutions. All right. So let's quickly jump in. Now let's go through step by step. Okay. The idea of problem solving using the kinematics equations. The big thing is you need to know, after reading the problem, you need to know what your problem is before you can start finding a solution. After you fully understand the problem, then you can go to your toolbox, which are your 4 big kinematics equations, find the correct equation featuring the correct variables, applying that, and solving for your unknown. After you have found a solution, you kind of need to make sure your solution makes sense. So all of that is the framework of the problem-solving skill set. So I'm going to start with step 1 with this problem over here, Captain Levi, if you know the reference on Attack on Titan. All right, so Captain Levi started from rest, and we talked about this in the previous video, one of the previous video about wording. If something starts from rest, we know that the velocity that's being talked about is 0, and since we are talking about starting, we mean here the initial velocity is 0, okay? And next we have he is accelerating, meaning there is some sort of an acceleration happening, okay? Then we have he is accelerating to a final velocity of 21 meters over the course of 3.6 seconds, okay? Now, one thing when you are reading a problem, let's say I don't tell you final velocity. I don't tell you this word. He accelerated to 21 meters per second. Now, if you don't have the wording, you can always use the units as a way of telling what you are given, okay? So this one, we know this is final velocity. That's what it is. Over the course of 3.6 seconds, which is our time, and we know that because the word after the number, you see the units, and that tells you what it is. And the question is asking for the distance that he covered. So the distance or displacement, it's not that, it doesn't really matter in this case because he won't be going backwards. He would just be going forward, okay? So this is what we're looking for. That is step 1. We need to read, and if we need to, we might need to reread the question while highlighting key information. So numbers with units, some keywords. We got some keywords, we got units, numbers with units, and as I mentioned, good idea to use units as a way to help you identify what you have. Next step we have is part 2. So part 2 here is to draw a picture to help you visualize the motion and or the problem. And what I am also going to add is I am going to say you must label your directions in this step, okay? Now, I went into depths into saying how important direction is in kinematics and in all units of physics. Direction is so important, and it will tell you whether or not you want to use a positive or a negative value in your question. So please label the directions, okay? So let's draw a picture first, and we have Captain Levi. Captain Levi started from rest, and he accelerated to a final velocity, and I'm going to draw that using arrows. He starts out with a small velocity, and then the velocity gets larger and larger and larger as he accelerates to a final velocity of 21 meters per second. And I am going to label towards the right here as the positive direction. If the question doesn't say right, left, or whatnot, you don't need to worry. You can you can use your own directions as you prefer. The next step is to write down your knowns that relate to these variables, the SUVAT variables. And also you want to identify what the question is asking for or what your unknown is. So we know that Levi starts off here, and I like to draw it. I have to label this beside the picture, so that kind of tells me where things are. He starts off with 0 meters per second. He travels for a total of 3.6 seconds, okay? And he achieves this final velocity here of 21 meters per second. We want to find out what this distance is that he has covered, okay? So that is identifying what you know and what you don't know. The next step we have is, now that we know our problem, we can now try to find something in our toolbox that we can use. So what I like to do is, when I am doing these problems, I like to have the equations right beside me. So I'm going to quickly write them down. Based on what we have, let's see which equation best suits our needs. So we have initial, time, final velocity, and we need the displacement. So if we go to our 4 equations, what we want to do, and this is important for you for all your kinematics equations, to find which equation has all the symbols that you have labeled, including your unknown, and your unknowns. The one that we are looking at is this second one over here, because we have the time, we have the initial velocity, we have the final velocity, and this is our unknown. The 4 variables are featured in that equation for us to use. That is the one that you want to use, okay? So I'm going to write that down, okay? And I also will choose this over this one over here, because you might think, wait a minute, isn't there this equation here? Your velocity equals your displacement over time. Now, if we go back to what I talked about earlier in the previous video, a main misconception is to use that equation when there is acceleration. When there is acceleration, you cannot use that at all. So this is another reason why I decided to make this problem for you to try, is because some people will be tempted to use this equation when it does not apply, because there is acceleration. Acceleration is not 0. Okay, so please don't get into that trap. Let's write this down. Now, you're very lucky in this problem because you don't have to rearrange for anything. You can just substitute in the values and solve for your displacement. So let's do that right now. So that's step 5 over here, substituting your unknown values in your formulae. Putting this in our calculator, we get 37.8 meters, which we will need to round it to 2 significant figures based on this problem, because everything was 2 sig figs. So 38 meters in the positive direction. So positive is not necessary. You could put it in if you want to. Now, that's what we got. We substituted values. We got our final answer. Are we done? No, we are not done. We need to evaluate our answer. So how to evaluate your answer? You've barely done any physics up till now. It's still very hard to visualize a few things, but we try our best, okay? So first things first, make sure that you have the correct sign or direction. If you've got a negative value for this answer over here, you know something's wrong, okay? So we can check off the direction there. We can also talk about the units, okay? So do we have the right units? And we can do that by checking our calculations, whether or not units will cancel out. So I have meters over seconds plus meters over seconds, which just leaves us meters per seconds, times the time, which is in seconds. Seconds cancel out, leaving us with meters. So we can say that is correct as well. Now, does this make any physical sense? At this time, I don't expect you to be able to do that to a certain degree, but just try your best. 38 meters, think of it as about the size of about 2 classrooms, the long side of 2 classrooms put together, roughly, okay? And considering he only did that in 3.6 seconds, which is not a lot of time, I think it might be possible, potentially. So that's kind of the best that you can think about right now, and that's okay. So we've done our check. We are now finished, okay? So that is the 6 steps to problem solving. I encourage you to try the next problem. Always don't forget you can write your equations on the side to remind you. What I'm going to do is ask you to pause the video, try this next one, and if you're having any trouble, you can always unpause and watch the rest of the video. Good time to pause. So here we have a problem where we first need to label our knowns in the problem, meaning that we have Mikasa accelerating from rest. So we know she's accelerating. She starts from rest, which is her initial velocity of 0 meters per second, the time of 2.9 seconds over, and the distance, the same as the previous problem, the same distance in the last problem, 7.9 meters, unrounded, because we want to make sure we don't round until the last step when we do the calculations of any problem. We are trying to find the final velocity. Here in the diagram, I label the forward direction being positive. Here are our knowns, and an unknown is our final velocity, and we know everything in between, the s displacement and the time. And here we're just writing down all the equations so we have it beside us to identify what we have and we don't have. Seems like we're looking at the second equation again, writing that one down, but we're solving for the final velocity, so we need to rearrange for final velocity, multiply both sides by 2. We also know the initial velocity is 0. We can get rid of that in that term. So rearranging that, notice the u just went away, and isolating for v, we divided by time on both sides. Now we can substitute our values in, using non-rounded value of our displacement, giving us 26 meters per second. Now we're checking our answers, and we have positive for our direction and meters per second for our units, which makes sense. All right, so welcome back. Here's the current problem that we have finished. Notice we use the same displacement or distance we've covered in the last problem. What I want to talk about is the evaluation of your answer at the end. So we definitely did. We're able to confirm the direction and the units. Now, there's a way how you can make a little bit physical sense of the answer you got, and that is from relating it to the previous problem. Now, Mikasa, who was the person in this problem, she took less time, 2.9 seconds, to cover the same distance Levi did, which means that the only way for her to have done that was for her to accelerate to a larger final velocity than Levi, which is the case because Levi's acceleration at the end, velocity at the end was 21 meters per second, taking a longer time. So 26 meters per second makes sense because it's larger than Levi's, so that she could achieve that distance in a shorter period of time. All right, so great job for getting through part 3. And I would say that we've just kind of scratched the surface. We've really only just done 1 out of the 4 equations. There is so much more to practice, to get better at. So I recommend practice. Please practice. The next video, I'm going to go over another example. And of course, you can just try that example and just look at the solutions at the end. But please tune in, although it is optional for you to watch that one. Okay? So, thank you for watching, and I will see you back for the next part 4.